Okay, here's the setup. Don't worry, I'm not using the Tektronix scope or any of this stuff right now. This is Tar Baby 5 IRF PG50 MOSFETs. We're going to be powering the bias with the negative DC just coming from the power supply because it's the easiest one to control. Okay, so I've got one oscilloscope probe directly across my little commercial current viewing resistor of 0.2 ohms right there, and I've got the other probe looking at the battery from the negative. These 2 points are electrically connected by a little bus underneath the board there, so they're not far apart electrically. Haha. And so we're looking at the battery with one probe and the current viewing resistor with the other probe. These, of course, are the two traces that we multiply together to get a negative power product. Okay, and we're supplying the bias with the potentiometer with a 10 ohm resistor, and we're bypassing the 50R in series. Okay, so we just have the 10 ohm resistor, and the pot's actually cranked all the way over to one side, so it's kind of irrelevant. We're just going to be using the power from the voltage control and the power supply to control the bias. Okay, so that's where the baselines are, right there. The A channel is the battery, okay, or the positive rail where it goes into the board. Sorry about the light. And we're viewing it at 50 volts per division, 10x attenuated probe, remember. And the B channel, its baseline is that gradical marker right there. Let me make sure it's right on it. Right there. The B channel is the current viewing resistor. Okay, so now let's see, there's the battery voltage, no load, and there's the current on the inline ammeter. So what I'm going to do now is just plug the battery in for the system. Alright, and boom, there you see the battery voltage goes up just about one full division, as it should, just slightly under one full division because we're at 49.6 volts, right? Right, okay, so now I'm going to turn on the bias current, on and on and on. There you see the oscillations, nice robust oscillations on both. Now we will, let's see if we can catch those oscillations. Have to change the time base. Okay, so we got the oscillations. You can see there's a bunch of little ripplies up there on the top. That's because I got a lot of voltage on there. Let me turn down the Elenco a little bit. And usually what I like to go is get about 15 milliamps on this guy for this demonstration. Okay, so now there's a little bit less ripple on the top there. Now remember where that negative line is. Right, it's right on that gradical marker. So I can tell you from long experience doing this that this times this is going to produce a negative power product. I think it's pretty easy to see. There's a lot of area underneath the line, meaning a negative current, right? And then when that's multiplied by the battery ripple, you will get a negative power product, I promise you. And pretty strongly negative too. Okay, and that's, you can tell that just from the difference in these areas and the difference in heights and widths of these curves here. And my oscilloscope does not like that signal either. Okay, so anyhow, this proves, I hope, that the circuit is actually oscillating, right? I mean, we're in the Ainsley oscillation negative power mode, right? Okay, so now what I'm going to do is disconnect. I'm not going to change anything. I'm just going to disconnect the oscilloscope probes, right? First I'll disconnect the battery probe, and the reason I'm doing this is because I'm going to measure a signal now that has a different ground reference. Okay, so now what I want to do is look at the current across this, or the voltage drop across this inline resistor here. That's a 10 ohm resistor, 10.3 ohms actually. So let's go ahead and put this in here, and we'll just hook this probe. We'll start at the potentiometer end and then hook to the other end of the resistor there. Okay. You try this with one hand. Okay. So now we're just directly across that 10 ohm resistor is a current viewing resistor. And that is going to be on the B channel. So already we have some stuff going on here, right? So let's just go to ground the channel for a moment. And let's look at where the ground line is. Okay, there's the ground right there. Okay, and we are at, on that channel, we're at half a volt per division, so let's go ahead and go to 1 volt per division. There's our line right there. Now let's unground the channel. Boom. Woo. Holy moly. So do you see how that dropped there? And there's our oscillations, if I can catch them, get them triggered. I can't catch it with the trigger. But those are our oscillations on the B channel. Get a little bit more amplitude on that. Maybe I can get them. Yeah, there they are. There they are down there. So what I've done is I've gone again to half a volt per division. So you can see that there's 1, 2, 3, and if you draw a line right across there, there's 3.5 full divisions at half a volt per division going through there. Right? Can that be right? 0.5 volts per division. 1, 2, 3.5 at half a volt per division. That's a lot of current. That's 10 times what I'm indicating over here. That can't be right, can it? Well, what am I doing wrong here? Oh, it's a 10 ohm resistor. Duh. Gotcha. So I'm indicating 150, or rather 1.5 volts, and it's a 10 ohm resistor. So I divide by 10. So what's my current? 150, 170 milliamps maybe? Yeah. And the reason that it's going down like that is because we have the probe at the potentiometer end, which is getting the negative voltage from the power supply, and the reference lead at the other end. So we're going actually from negative to positive across that probe, which gives us the negative indication of the current. Okay? Now I hope that this is enough to establish that if we use an external power supply as a bias source, current does flow. We are flowing current, DC current, with the oscillations rippling on top of that. Okay? Now, will it do the same thing if I use a function generator to provide a long DC pulse, like a 2-minute pulse? I think it will. Thanks for watching. 1, 2, 3.5 at half a volt per division is 1.75 volts, and then a 10.3 ohm resistor gives you 175 milliamps. Thank you for watching.